Welcome back to CS Connect series. In the last video, we covered about propositional logic content. In this video, we are going to apply the knowledge that we have got from propositional logic into certain application areas. First, we are actually starting with logic and bit operations. Computers represent information using bits. What are the bits available? 0 and 1. Only 2 bits are there. In logic, a bit can be used to represent a truth value. So what is the truth value that we know from proposition? Truth values can be either false or true. So this false can be equated to 0 and this true can be equated to 1. So whenever we say it's false, we can represent it using 0 bit. Whenever we say it is true, we can represent it using 1 bit. A variable is called a Boolean variable if its value is either true or false. Consequently, a Boolean variable can be represented using a bit. So if a variable is going to have the value of 1, we can say it is true. When it is going to have a value of 0, we can say it is false. Computer bit operations correspond to the logical connectives. So let's take P and Q. So we are replacing T by 1 and F by 0. We get this. So wherever we have true, 1 is getting replaced. Wherever we had false, 0 is getting replaced. Now we'll get on to the logical operation. P and Q. So we have true, triple false. So P and Q will be 1 and triple 0. So instead of this conjunction, we are using AND here. Now we'll get on to disjunction. Only the last row is false. Only the last row will have 0. So this disjunction operator or inclusive OR is OR here. What about XOR? That is exclusive OR. So here we can mention 0 in first and last row. So this is XOR operation. Disjunction becomes OR, conjunction is and exclusive OR is XOR. So we can extend bit operations to bit strings. What is actually a bit string? A bit string is a sequence of 0 or more bits. The length of the string is the number of bits in the string. So usually we say it is represented by 0 or 1. When I say bit string, it can be a set of numbers for representing binary codes and everything we have been seeing so far in the CS Connect series. So that can be treated as a bit string. Now we will take 2 bit string with random zeros and 1 values. There is no meaning for that. If you want, you can convert this into decimal also. But my intention is to show you how bitwise logic operation is going to take place. When we apply logic operation for these 2 bit strings, it has to operate bit by bit. When the logical operation is applied bit by bit, we call it as bitwise OR, bitwise and bitwise XOR. So if you take OR operation, 1 or 1 will give you 1, 0 or 1 will give you 1, 0 or 1 will give you 1, 1 or 0 will give you 1. This is the result. What about AND? 1 and 1 will give you 1, 0 and 1 and 0 will give you 0 only. What about XOR? The first bit is 1 in both the strings. So this will be 0. Here we have alternate values 0, 1, 0, 1, 1, 0. So the remaining places we will have 1. This is just to show you how we are connecting propositional logic to binary logic content in computer science. Now we are getting into the applications of propositional logic. We can translate English sentences into language of logic. In order to specify requirements for software and hardware, we have to express it in a logic language, we can say. Apart from this, in order to design computer circuits, you will need this logic because the basic hardware is depending on this particular logic operation. Then to construct computer programs, only when you understand logic, you can go for problem solving. Verify the correctness of programs. So once you construct programs, automatically the correctness of the programs can also be verified using the same logic only. Build expert systems. Whatever you ask, it has to process and give you some answer. Analyze and solve many familiar puzzles. So we'll get into translating English sentences. Translate sentences into compound statements. This will remove the ambiguity and make them precise. It removes ambiguity means you cannot take it in the meaning that you like or you understand or you perceive. It all depends on how they wanted to express to you. The same thing you have to understand. It is removing ambiguity. At the same time, it is making it precise. It means we are making it clear. Let's take an English sentence. You can access the internet from campus only if you are a computer science major or you are not a freshman. Now, what are the different propositions that you can infer from this particular statement? We have to represent each sentence part by propositional variables. So first we will try to take the proposition. You can access the internet from the campus will be one statement. You are a computer science major will be another statement. You are a freshman. You should not include not here because it is negation operator. You are a freshman will be the third statement. Access the internet from campus can be taken as propositional variable A. Computer science major is what I have written as computer major here. So you can take it as computer science major. This is C. And you are a freshman becomes F. So I have not used the conventional PQRS variable in order to understand the statement better. Access for A, computer science for C and freshman for F. In order to make it meaningful, I have taken it as A, C and F. So the first step is to represent each sentence by propositional variable. The second step is determine the appropriate logical connectives between them. If you take freshman, they have used not. This is one logical operation. They have used or. This is one logical operation, disjunction. And they have given only if. This is conditional statement. This is another logical operation. So first we will start with freshman. You are not a freshman means negation of F proposition. So it is negation of F. You are a computer science major or you are not a freshman. Only this part. This can be translated as computer science major is C or is disjunction. Not a freshman will be negation of F. What about the first part? You can access the internet from campus only if some condition is there. Access the internet from campus is actually propositional variable A. Only if means you are using implies operator, and here the condition I have just specified in brackets. I have not included the second part of the sentence in order to make it clear for you. Remember, P implies Q can also be expressed as P only if Q. Now what do you find here? A only if the condition. So A is treated as the hypothesis and this particular expression in the bracket will be treated as the conclusion. So what is the logical representation? Instead of P implies Q, instead of P I am going to apply A. So it is A implies. What is the Q part here? It is you are a computer science major. C disjunction negation of F. So it will be C or negation of F. This will be the logical representation of the English sentence. We will get into system specification. Now we will express this particular specification using logical connectors. The automated reply cannot be sent when the file system is full. You have two kinds of proposition here. The automated reply has to be sent. The file system is full. Here you have when. What does this when say? It's a conditional statement. We have to represent the sentence using propositional variables. So we are splitting it to two sentences. One statement will be the automated reply can be sent. You should not take the not part. It is going to involve negation operation. The file system is full is taken as the other proposition. So automated reply is hinted as A. File system is hinted as F. Now the second step. We have to use appropriate logical connectives. So what is the first connective that we have to apply here? Cannot. So it is going to be negation of A. And when we use when, we have something called implies operator. The automated reply cannot be sent is represented by negation of A. When the file system is full is represented by F implies. Why do we not represent it as implies F and why are we using F implies? We have to remember Q when P can be represented by P implies Q. What is Q here? Automated reply cannot be sent when system is full. So it is negation of A when F. How do you actually represent it using implication operator? It is P implies Q. So what is P here? It is F implies what is Q? It is negation of A. This is how you will be representing it logically. So this is going to be Q and this is going to be P. What is this Q? We know it is negation of A. What is this P? It is F. How do you represent Q and P? It is P implies Q. So how do you represent similarly? P becomes F, Q becomes negation of A. This is how you have to translate. That's why I gave you all possible English expressions of P implies Q. If you don't get the meaning, you will mark it in reverse order like negation of A implies F, which is actually wrong. So we have some additional points here. System specifications should be consistent. That is, they should not contain conflicting requirements that could be used to derive a contradiction. When specifications are not consistent, there would be no way to develop a system that satisfies all specifications. Say for example, we have A, C, F in the previous example. We have to list the condition in such way that when A is true, when C is false and when F is true, when all these three specifications are consistent, it should satisfy and end up with true value at last. When they don't give you true value, it means the specifications are not consistent, or we can say that system does not satisfy all the specification. How to determine whether a set of system specifications are consistent? We have to represent the specification using logical expression. An assignment of truth value should make all the specification to be true. It means you have to check when A is true, what will happen? When A is false, what will happen? Similarly, when C is false, what will happen? When C is true, what will happen? If you are going to get a truth table of A, C, F, so altogether you will get 8 possibilities out of 3 variables. So this is all for A true. And similarly you will have 4 false value and the same set of C and F value will repeat. It's TT, FF, then we have TF, TF. So you have 8 values. They are asking for which set of values you will have true in the final column after applying all the operation. That is what they say. An assignment of truth value should make all specifications to be true. So which value of A, which value of C and which value of F? You are going to have only 2 values. It is either true or false. But on what combination out of these 8 rows, which row will give you true? That is what they are asking. We conclude that these specifications are consistent when you are able to derive true. We can also examine the assignment of truth values using a truth table. That's what we do here. But till 3 variables, it goes for 8 rows. When you take 4 variables, it will go for 16 rows. When you take 5 variables, it will go for 32 rows. There is also a possibility where you will never get true in the final column. If that is the case, we can say the specifications are not consistent. When you don't get true anywhere, it is not consistent. Wherever you get true in the final column, that time we can say it is consistent. Now we will get into the practice problem session. Find the bitwise OR, bitwise AND, bitwise XOR, that is exclusive OR, of each of these pairs of bit strings. They have given 7-bit string in A, 8-bit string in B, 10-bit string in C and 10-bit string again in D. We have to find AND OR, which is quite easy. For XOR alone I have given the table here. Whenever you have same values, you have to end up with false. So now let's start with the first one. 101 111 is the first string. 010 0001 will be the second string. So what is the bitwise OR? Whenever you have zeros together, it should be 0. The rest of the places it is 1. 1 or 0 will give 1. 0 or 1 will give 1. 1 or 0 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 will give 1. 0 or 1 will give 1. So all the bits are 1 here. What about bitwise AND? Only when you have 1 in both the places, you should get 1. The rest of the places, it is 0. 1 and 0 is 0, 0 and 1 is 0, 1 and 0 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 is 0, 0 and 1 is 0. So bitwise AND is totally 0. Now let's get into XOR. Do you have same values like 1 and 1 or 0 and 0 anywhere? Nowhere you have such combination. So everything is going to have 1 here. So both the inclusive OR and exclusive OR operation is giving 1 here. What about the B problem? We have 4 ones and 4 zeros in the first string and 1 0 1 0 1 0 1 0 in the second string. Now we'll go for bitwise OR. 1 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1. 0 or 0 will alone give you 0. 0 or 1 is 1, 0 or 0 is 0. For OR operation, let me just give you true, true, true and false. So wherever you have true, you have to substitute with 1. What about the AND operation? Only true and true will give you true. The remaining 3 rows will give you false. So wherever you have true, just use 1. Wherever you have false, just use 0. I am afraid actually to put arrow mark in this video because everything will be interpreted as implication or by implication, but just understand it's just a replacement. Okay. Now let's get into AND. You have 1 and 1 here, so we will have 1. Then 1 and 1 here, we will have 1. The rest of the places you have alternate zeros and ones, and here you have completely zeros. So the rest of the places you will have zeros. What about bitwise XOR? So just find where you can have 0 0 and 1 1. So you have 2 places with 1 and 1, mark them with zeros. Then you have 2 places with 0 and 0, so mark them with 0 again. So 4 bits are changed as 0. 1 XOR 0 is 1, 1 XOR 0 is 1, 0 XOR 1 is 1, 0 XOR 1 is 1. So this will be the bitwise XOR answer. What about the C? So for bitwise OR, wherever you have 0 0, there alone you can place 0. So you can place 1 in the rest of the places. What about bitwise AND? Just find 1 and 1 combo. Here alone you will have 1. So the remaining places will have 0. What about XOR? Just find where you have 0 0 1 1 combo. You have 0 0 1 1 combo in these 3 cells. So this will become 0 ultimately. Similarly, in these 2 cells you have 0 0. Let me give you in this way so that you can map it correctly. Similarly, these 2 values and these 2 values. So this will also give you 0. The rest of the places are alternates of 0 and 1. So you can place 1 clearly here. Now the final one. You have complete ones in the first string and complete 0 in the second string. So what is bitwise OR? This is going to give you 1 because there is no 0 0 combination. Similarly, if you take bitwise XOR, it does not have 1 1 combo and 0 0 combo. So this will also give you 1. Now what about bitwise AND? 1 and 1 can alone give you 1. So this will definitely turn to be 0 for all the bits. Next problem. Express these system specifications using the propositions together with logical connectives which can include negations. What is the proposition P? The message is scanned for viruses. What is the proposition Q? The message was sent from an unknown system. The message is scanned for viruses. It is P whenever the message was sent from an unknown system. So it is P whenever Q in this form. When we have Q whenever P, it is P implies Q. When we say P whenever Q, it is actually Q implies P. So this is of the form P whenever Q, and so we have the form Q implies P. So since whenever means if, so this is also taken to be P if Q. For this particular P implies Q, we can also say this as Q if P. This is for P implies Q and this is for Q implies P. The second one, the message was sent from an unknown system. This is Q. but it was not scanned for virus. But means you have and, not scanned for virus means it is negation of P. So it was not scanned for viruses. This will be negation of P, and now but means and. So Q and negation of P. What about the C statement? When a message is not sent from an unknown system, it is actually when negation of Q, it is not sent. So it is negation of Q. It is not scanned for viruses, negation of P. Message is not sent from an unknown system and it is not scanned for viruses is for negation of prepositions. This is of the form, I am just rearranging this. Negation of P is there standalone, but when is going to come with negation of Q. So this is when negation of Q. This is going to be together. Negation of P is going to stand aloof. Here it is when P. When means if. So it is actually negation of P if negation of Q, or negation of P when negation of Q. So when we say Q when P, this becomes P implies Q. When we say negation of P if negation of Q, this will become negation of Q implies negation of P. This particular phrase, this will just interchange the propositional variables with conditional operator. Same thing, here you have negation of P when negation of Q. So this will also interchange the preposition using the implication operator. This is how we are equating it to negation of Q implies negation of P. Now the final problem. Are these system specifications consistent? So during the explanation, I just told you how to find whether it's consistent or not. Now this is the working problem. What are the prepositions that you can take from these specifications? Let me first read all those specifications. The system is in multi-user state if and only if it is operating normally. If the system is operating normally, the kernel is functioning. The kernel is not functioning, or the system is in interrupt mode. If the system is not in multi-user state, then it is in interrupt mode. The system is not in interrupt mode. So I have just marked the logical operation terms alone. So we have some statements. System is in multi-user state. System is operating normally. Kernel is functioning. System is in interrupt mode. So let's take the proposition. The system is in multi-user state. Keeping the term multi-user, we will mark it as proposition variable M. Then we have the system is operating normally. We will take normal operation into consideration, take it as N. The kernel is functioning. Specifying kernel, we will mark it as K. The system is in interrupt mode. Taking interrupt to be the keyword, we will use I here. So we have derived the four prepositions. Now we have to convert them to logical expression. The system is in multi-user state if and only if. This is actually by implication operator. So first we will try to substitute the variables. The system is in multi-user state will be M. If and only if will stay as it is. What about it is operating normally? It's actually the system is operating normally, so we are taking N. M if and only if N. This is the first statement that we are getting. So I am not directly using the logical operation. I am just trying to use the propositional variable first and then go with the logical expression. The next statement, if the system is operating normally, it means if N, the kernel is functioning will be K. So if N comma K, this is equivalent to if N then K. You can take it that way. Now the kernel is not functioning. It means negation of K or disjunction operation. The system is in interrupt mode. This is I. So we can say not K or I. What about the next one? If the system is not in multi-user state. So if not M, then it is I. So if not N, it is I. What about the final one? The system is not in interrupt mode is negation of I. Now we will just go for the logical expression. What is if and only if? It is by implication operator, so we go with m by implies n. What about if n then k? N implies k. What about not k or I? It is negation of k, the disjunction operator along with I. What is if not m then I? Not m is actually negation of m. If means you are using implies operator. So not m implies I. What is not I? It is negation of I. Now what you can do is you have four variables. One way of checking the consistency is go for the 4 variable truth table, find negation of I, then all the other 4 expressions together and combine them with AND operator. So you have to find m by implies n, then you have to find n implies k, then you have to find negation of k or I, then you have to find negation of m implies I, then negation of I. Once you find the values for all these columns, you have to combine the results using conjunction operator. When you have true everywhere, that will alone give you true in the final column. But if you don't get true everywhere, you will end up with inconsistent state. So after this, I'll just try to show you in truth table form. Now let's number the specification as 1, 2, 3, 4, 5. Only when I is equal to false, 5 can be true. So we have to make sure that all these specifications should turn true. It means all these should result in true. Only then when you combine them with AND operation finally you will get true. Even if one turns out to be false, you cannot have consistency there. So if I is equal to F, negation of I will become true. So for that what will be the value of I? It is false. Only then this particular specification will turn true. So we are starting with a single variable. So from this I must be false. So we know the value of I is equal to false. What is P implies Q? When P is false, Q can be either true or false. So we are going to use this for the next one. In order for the fourth specification, negation of M implies I to be true. We already know I is false. Just take this to be negation of M here as P and I is going to be false. Negation of M should not be true. If this is going to be true and false, this specification will turn false. So here we have to make negation of M to be false, because when negation of M is false, we need not worry about Q being true or false. So we know I is already false. So this negation of M should also be false. When negation of M should be false, what is the value of M? M must be true. So in order to make this specification true, we are setting the value of M to be true. Now we got the value of two variables. Now we will get into by implication. P by implies Q is true when both P and Q have the same truth value. Both can either be true or both can be false. Since we want the first specification, that is M by implies to be true, it implies that N must also be true. Why? Because we know M is already true. When I have true here, only a true value can give you true totally for this particular specification. So by this by implication operator, we are making sure N will also be true. So N is equal to true here. Now the next one, since we want N implies K to be true, it means we know the hypothesis is true now, implies this should not be false. If T implies false, that is P implies Q, where P is true and Q is false, you will have false. So automatically when the hypothesis is true, the conclusion should also be true, which will make K also to be true in order to make this particular specification true. So from this we have the value of K to be true. So K is equal to true. Now all the variables have a specific truth value. Now we have the third specification. If you apply negation of K and I value in this particular specification, it should give you true. If it gives you true, the system is consistent. If it does not give you true, the system is not consistent. Let's take 3. So we know k is true, I is false. What is negation of k? It is false. What is false or false? It will give you false ultimately. Since it is giving false, we are concluding that the system is not consistent. So little by little, we are trying to make every specification true. From fifth one, we are moving to fourth one. From there, we are moving to first one. Then from first, we are moving to the second specification. We are finding all the 4 values. But when we substitute those values in specification 3, this is becoming false because false or false will give you false. Since one of the specifications is false, which one? It is third specification. We are concluding it is not consistent. So I will also show you in truth table format. So what is m by implies n? So the first 4 value we will have true. Then the last 4 value we will have true. What about implies operation? Whenever n is t and k is false, we will have false. The rest of the value we will have true. Now we will move to negation of I. So we have to just reverse them. Ft, Ft. Now we have negation of k or I. So what is negation of k? We have F, F, then T, T. So I'll just write the I value also here so that it will be easy for you to compute. It's a simple disjunction operation. So whenever you have F and F, you go with F. For the remaining options, you have to go with T. What about negation of M? You have to make false for the first 8 rows. Then we have true for the last 8 rows. Now we have to go with I value again. Now we have to see a condition where hypothesis is true and conclusion is false for this implication operator. The first 8 rows will have true only. What about T and F? You have here it is F, it is F, it is F and it is F. So the remaining places will have true. Now you have to combine all the conditions together. It means M by implies N and N implies K and negation of K or I and negation of M implies I and negation of I. Whenever you have true in all the 5 columns, that alone will give you true in the final column. We have true, 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 true and false here. So this is false. True, true, false, true, true. Even if you find one false there, it will end up with false. Because we know true and true will give true. The remaining rows, true and false, false and true, false and false, all this will yield false. Even if one condition turns to be false, everything will end up with false. Here we have 2 false, so again we will end up with false. Then you have 1 false here. The remaining 4 are true, no use. Wherever you have F in the first column, you can blindly write F because you need not check the others. What about the last 4? You have T in first 2 columns, no issues. What about this T, F is here, so it's false. Here it is false, false and true, it is false. It is true, true and false again, so it's false. Here it is true, false and true. So can you understand? All the resultant row is giving you false, which is telling you that the system is not consistent. When can you conclude that the system is consistent? You will not get true in all the 16 rows. In any of the row, you will get true. So which value is yielding true, that particular row alone you have to take. Just for example, I am telling you, this row is going to give you true in the last means. For example, then we can take M value to be true, N value to be false, K value to be false, I value to be true. For this set of combination, we can say those specifications are true and so the final value is also true, stating that the system is consistent. But such a scenario has not occurred in this particular question. If there are 4 or 5 variables, you cannot go keep on checking in some timed exam. Find the values of all the propositional variable and try to apply them in every specification and check all the specification are going to give you true. Since we don't get true for the third specification, since it turns out to be false, and even in the truth table, since we found all the 16 rows are giving false, we are concluding that this system is not consistent. With this problem, we are completing this video. I'll meet you in the next video. Thank you, viewers.